let me just emphasize one thing that I need to emphasize. The quarks and the leptons, all of them have spin 1/2. We call them fermions, named after the Italian physicist Enrico Fermi, who was one of the great physicists of the 20th century. On the other hand, the forces between quarks and leptons are mediated or carried by these particles that have spin 1, gluons, photons, and W's and Z's, or spin 2, the gravitational force. Yes?
What is spin 1 and spin 2? What does that mean?
Okay, mathematically, we really understand what it means. What it actually means, I don't think anybody understands.
Okay.
But what it basically means is that, well, mathematically, I can't stop speaking. Mathematically, the idea is, remember when I said that quantum mechanics is mysterious, but it makes certain things simpler? Okay. So, the classical picture is that I could be spinning with an arbitrary velocity and my mass could be arbitrary. You know, I breathe in, my mass goes up slightly by the amount of oxygen and nitrogen I've breathed in. And the speed at which I rotate is basically arbitrary. So the angular momentum or spin that I could have is just completely arbitrary. All right. When you apply our understanding of quantum mechanics, our mathematical understanding of quantum mechanics, it turns out that the amount of angular momentum a particle can have is 0, h bar over 2, h bar, 3/2 h bar, 2 h bar, 5/2 h bar, 3 h bar, and so forth. Multiples, integral multiples of a half h bar, or integral multiples of Planck's constant divided by 4 pi. This follows from the mathematics pretty neatly. In fact, I wrote a book called Physical Mathematics in which I worked this stuff out. But I don't understand it, and I don't think anybody does.
So why is it called spin?
Oh, just because. All right, it's caused spin. Good question. I owe you a lot of candies. It's caused. Good catch. It's called spin just to distinguish in other words, every electron always has angular momentum, Planck's constant over 4 pi, always. Each electron, though, may be moving in a particular way about some axis and have what we call orbital angular momentum. So in other words, if an electron shoots here and there's a magnetic field pointing down, then it's going to go around, if I've got the sign right, it'll go around in a circle. That is also angular momentum. So the electron has orbital angular momentum about the axis because of its motion. The spin is the intrinsic angular momentum that no matter what the electron is doing, it always has angular momentum about its own axis of Planck's constant divided by 4 pi. As I said, this is not understood, and the reason it's not understood is that we think of the electron as a point particle in most theories, the most well-developed theory, the theory that has any contact with experiment, quantum field theory, and quantum mechanics. The electron is a point particle, and it's hard to see how a point particle can have any angular momentum at all because there's no R. R cross P is angular momentum. There's no R. R is 0. So what probably will lead to an understanding of these and other things is a theory of elementary particles as extended objects. String theorists think of them as extended. Originally, the string is extended in one dimension. But we don't know if string theory is right. Let me, since we've got this demo set up, and since it's such a nice demo, even though I haven't finished explaining so many of the things that I wanted to talk about, I'm just going to do this demo. And for this demo, what we need to do is pass out, here, can you pass these out to yourself and the people up there? And then maybe you could pass out, pass out some of these, and all right. Oh, well, here, thank you. Right here. 2 of them at least. Okay, these are basically transmission gratings, and what I'm going to do now is turn on this demo, which is one of the nicer demos. As I said, quantum mechanics makes things I'm afraid to turn the lights out when he's walking around, because we could have an accident. So what we've got here is a high voltage supply, high voltage applied to hydrogen. And I think what's happening there is electrons are shooting through the hydrogen gas, exciting the hydrogen molecules, and these molecules then are, you would all do better if you were in the center. You can see? Okay, anyway, these are exciting these states. Remember I said for the hydrogen atom we can describe the quantum states very simply as E sub n is -1/2 m c squared alpha squared over n squared, n being an integer, alpha 1/137, and m c squared 0.5, well 511,000 electron volts. That comes out to a ground state when n is equal to 1, this is 13.6 electron volts. So the energy levels of the hydrogen atom are quantized. What we've got here is much more complicated because they're hydrogen molecules. And so let's see, I need one of the gratings. Does somebody have an extra grating, or do we have some?
I have one.
The box is over there.
Box is, all right, let me grab 1 or 2 of these. So, okay, what you do is this. You take your grating and you don't try to look directly at the light through the grating. You hold the grating off to one side. And if you hold the grating off to one side, here I shouldn't stand in the way. If you hold the grating off to one side, you will see a red line, but also a blue line. And the red, you will notice, is really red. And then there's a blue-green line, and then there's kind of a violet line. And that's why the red light there is not a pure red. Instead, it's a sort of a lovely shade of pink, which is a combination of pure red and a certain blue. And and you've got to hold the thing in landscape mode, and you hold it so that you're looking a few, maybe 20 degrees, so that the angle from your eye to the transparencies makes an angle of about 20 degrees with your angle between the. In other words, one line is your eye to the bright red tube. The other line is your eye to the transparency. That should be about 20 degrees, 10 or 20 degrees. And what happens is this This transmission grating splits the colored light into specific colors, pure colors going in specific directions. And each of the pure colors has a pure frequency, a specific frequency, and that specific frequency times Planck's constant is the energy of the photon, and that energy is because the hydrogen molecule has undergone a transition from one electron state to another. The red line is lower energy than the green line, because the green line has, or the blue line I should say, has, the blue-green line has higher energy. And there are some faint red lines, and then there's the blue-green, and then there's some violet off to the right. All right, that's hydrogen. That's the prettiest one of these. But there are, as I switch the electrical potential from one to another and then turn it on. This is xenon. Xenon is a rare gas. In fact, you can see it up there in the periodic table. Xenon is this one right here. And so let's see what the I'm not getting much from xenon. Oh, here we are. Yeah, xenon, oh boy, that's very complicated. Even though xenon is monatomic, monatomic, in other words, it's a gas of atoms of xenon, what you can see is that there are just zillions of lines. So you see a whole band of violet, a band of green, a band of yellow, a band of orange, and some, not a hell of a lot of red, but some red. And the reason is, of course, that xenon has many, many electrons in this shell around the nucleus, and so there are all sorts of complicated electronic transitions. So all sorts of color frequencies are possible. All right, that was that. If we go to, let's go to water vapor. So water vapor is very much like hydrogen, and I guess that's not surprising because it's H2O, and so those are hydrogen transitions, but not all of them because we see new lines. The orange wasn't there in hydrogen, and the blue lines are more obvious. And if we had eyes that were sensitive to infrared, we'd see infrared lines. And that's why water is a greenhouse gas. Let me quickly go to CO2. We're actually running out of time, but there's CO2. And now if you look at CO2, boy, you see it's almost like xenon. There's a huge violet band, a green band, an orange band, and some red. And as I said, if we had infrared eyes, we'd see that the CO2 had lots of lines in the infrared.